So this is a example of pure ALOHA. Suppose the stations on a wireless ALOHA network are a maximum of 600 km apart. If we assume that signals propagate at 3 into 10 to the power 8 milliseconds, then we have to find out the propagation time. Okay, so this is the propagation time, that is Tp equal to 600 into 10 to the power 5 divided by this one. So this is 2 milliseconds. Okay, so this is the propagation time. And if k equal to, so for different values of k we can get different means result. Okay. So how many times we are attempting, that is our k. So according to our k, we will generate the value of this random number. It can be 0 to 2 to the power k minus 1. So if k is equal to 1, so you will get some different result. If k equal to 2, you will get some different result. So your attempting number is actually very much important for choosing the random number. What should be the random number, and using those random number you can calculate this waiting time. Okay. So now this is the vulnerable time for pure ALOHA protocol. So see here, the B's end collides with A's beginning. See, A's, this is the A's frame and this is for B's frame, and the end of this B is colliding with starting of A. So this is the vulnerable period. Okay. So vulnerable time, and similarly for C also, the starting time of C and ending time of A is the same. So this is also the vulnerable time. So here you should know that what is the formula of vulnerable time. This is 2 into FR. Okay. So what is TFR? TFR is equal to average transmission time for a frame. So you need to wait for an average transmission, the transmission time. Okay, that means to reach a frame to its destinations, what is the time it's required to transmit the frame. So that time you need to provide. So average transmission time for a frame is TR. Okay, so the vulnerable time is what? That is 2 into TFR. Okay, so this is the vulnerable time. If you are sending the data at that time, then there are a chance to collide these different types of packets. So you have to wait when a station is sending a data, just calculate the vulnerable time, and another frame needs to wait, okay, for that time period, and after that the different stations can send the data. So this time is called vulnerable time, when that means the time it's take to reach a frame from its sender, from a source to a destinations. So another stations needs to wait for that amount of time. Okay, because if at the same time the station wants to sending the data, then there is a high chance to be a collisions. The collisions may occur. Okay, so a pure ALOHA network transmit 200 bits frames on a shared channel of 200 kbps. What is the requirement to make is frame collision free? Okay, so frame collision free means you have to calculate the vulnerable time, and the stations must be send the data. After that, suppose average transmission time is TFR is 200 bits by 200 kbps, or it is 1 milliseconds. So this is the vulnerable time is what? So this is the transmission time, and the vulnerable time is 2 into 1 millisecond, so 2 ms. So this means no station should send later than 1 ms before the station start transmissions, and no station should start sending durations the 1 millisecond period that the station is sending. Okay, so every station have to wait for this 2 milliseconds time. Okay, so this is the vulnerable time. So the throughput for a pure ALOHA is S equal to G into e to the power 2G. So this is the throughput. So maximum throughput is S max equal to 0.184. Okay. So when G is equal to half, G is equal to, when G is equal to 1 by 2, then we can get the maximum throughput. The efficiency should be maximum. So here G is what? Average number of frames generated by the system. Okay, so this is the throughput, and this is the value of G, and you can calculate the value of S, that is the throughput, that is equal to G into e to the power minus 2G. And for a pure ALOHA, the maximum throughput is S max equal to 0.184. So a pure ALOHA, this is an example. A pure ALOHA network transmits 200 bits frames on a shared channel of 200 kbps. What is the throughput if the system produces 1000 frames per second, 500 frames per second and 250 frames per second? Okay, so the frame transmission time is 200 by 200 kbps or 1 ms, and if the system creates 1000 frames per second, this is 1 frame per millisecond. Okay, so the load is 1 frame per millisecond, so load is 1. Okay, so here you will get 1 into e to the power 2 to the power 1, say it will 0.135, that is 13.5%. This means that throughput is 1000 into 0.135 equal to 135 frames. That means only 135 frames out of 1000 will probably survive. Okay, so other frames can be lost. So that is the efficiency, that is if we are sending 1000 frames, how many frames can survive, that is the main thing. Okay, so here we are getting that 135 frames, that means only 135 frames out of 1000 will probably survive. And if it is 500 frames per second, this is half frame per milliseconds. Okay, so the load is 1 by 2, and we will get as the value of S is equal to 0.184. That means G, the value of G is actually half. So this is actually S equal to 0.184, and this means the throughput is this 500 into 0.184, that is 92, and that means only 92 frames out of 500 will probably survive. Okay, so in this way we can calculate the throughput for different number of frames. So this is the diagram for slotted ALOHA network. So here slotted ALOHA, what we are doing in slotted ALOHA. So in pure ALOHA we have the vulnerable time is 2 into TFR. Okay, at the pure ALOHA, and so here in the pure ALOHA we don't have any, means we can when we have a data we can send the data, and if there is any problem, if the data is not sent properly, then we can calculate a random number of time according to our attempt number, and then we can just calculate our time. Okay, according to our propagation rate, we can calculate a time, and the frame has to wait for that amount of time and then resend. Okay, but in pure slotted ALOHA, what we can do, we can divide the time into slots of TFR. Okay, so here you have to divide the slot of TFR. Okay, and the you have the stations need to force the data only at the beginning of the time slot. Okay, they can send the data at the beginning of the time slot. You can see. So each and every time slot, this is the time slot 1, different time. The slotted ALOHA means the whole channels is divided into different slots. Okay, the whole channel is different time slot. So each and every station can only send the data only the starting of the time slot. See, each frame is starting can send the data, each stations can send the frames only on the starting of the time slot. Okay, so in the slotted ALOHA, the vulnerable time is TFR. Okay, and this is the throughput, that is S equal to G into e to the power minus G, and you have to remember it, and S max equal to 0.368. So this is the throughput for slotted ALOHA, and this is the throughput for pure ALOHA. Okay, so only difference is that S equal to G to the power e to the power G here, and in pure ALOHA we have e to the power minus 2G. Okay, so and the maximum throughput of slotted ALOHA is 0.368 when G equal to 1. So this is the vulnerable time for slotted ALOHA protocol. So here you can see this is the beginning, this is the end, and here those two stations are collide here. Okay, at the same time two different stations are sending the data. So here is the collisions. So this is the vulnerable time. So the vulnerable time is TFR, and vulnerable time for pure ALOHA that was 2 into TFR. So a slotted ALOHA network transmits 200 bit frames on a shared channel of 200 kbps. What is the throughput if the system produces? Same maths, but the formulas are different. Okay, so here G, you have to put G equal to e to the power minus C, and C for load 1 you can get S equal to 0.368, that is 36.8%. This means the throughput is 368 frames, only 386 frames out of 1000 will probably survive. Okay, so in this way for different frames, and using this formula you can calculate the throughput of this channel. So this is the space and time model of the collisions in CSMA. CSMA this is for carrier sense multiple access. So now we will talk about CSMA, carrier sense multiple access. Okay, so in carrier sense multiple access, this is the first model of space and time, where the collisions is actually we can show the collisions area. Okay, so here A, B, C, D different stations are here, and A can start at the time T1, this is the first time slot, and B can start also at T1 time, and C starts at T2 time. Okay, and D also can start the T2 time. So at the same time when two stations are attempting to access the channel, so collisions can arise. So the thing is that how we can avoid this type of situations. So that is carrier sense multiple access. That means you have to check the transmission line, that whether there is any carrier or not. That's why this is called carrier sense. You have to sense whether the carrier is present or not. Okay, so this is the vulnerable time in CSMA. This is the logical diagram. So here we have T1 and B sends here, B wants to send the data, B sends here, and C also sends here, and D also sends here. So at the same time they are, so this is the vulnerable time, this black portion, so this is the vulnerable time. Okay, that means at the same time they are accessing the station, they wants to access the station. So now for this carrier sense multiple access, we should provide some persistence methods. Okay, so persistence methods, we have different persistence method. So first one is one persistent, second one is non-persistent, and last one is p persistent. So what is one persistent? So one persistent method is what? One persistent method, this is very simple method, and even it is very straightforward method. So here when means after the stations finds the line is idle, then it sends the frame immediately. Okay, so it's sensing the stations, is sensing the channels, and obviously this is carrier sense multiple access. That means carrier you need to sense, that means you have to check whether the channel is free or not. So when the channel is free, at that time you are sending that means in one persistence the channel the stations need not wait, they sense it's the frame immediately with probability 1. Okay, that's why this is called one persistent. So in this method, when you are just sensing that the channel is free, the station immediately send the data. So what will happen in this method? Has the highest chance of collisions. Okay, because it may happen that two or more stations may find the line is idle and they can immediately send the data. So at the same time they are sensing the channel is idle and immediately they are sending the data. So the collisions, the probability of collisions is high here. So this is the first persistent. And non-persistent, the second method, this is the non-persistent. In non-persistent method, a stations that has a frame and they sense the line. Okay, and if the line is idle, then it can sense the data immediately, and if the channel is not idle, it waits a random amount of time and then sends the line again. Okay, so it sends at first, then it has to be wait, after that it sends again, then it needs to wait, and then it needs to transmit. Okay, so they are in non-persistent method, they are waiting for a random amount of time, and that is they are sensing the line again. If the line is idle, they are sensing the line. If the line is again busy, they have to wait, and in this approach it can reduces the chances of collisions. Okay, as because they are waiting for an amount of time, they are waiting for an amount of time. Okay, they are not sending the data immediately, they are waiting for an amount of time. Okay, so that's why the chances of collisions may decrease. And after that there is a, so these are the persistence method or CSMA. Okay, so remember it. So non-persistent and then p persistent. In p persistent method what will happen? So here also the whole channels is divided into different time slot. See, these are the different time slot, and continuously the channel continuously it is sensing whether the channel is busy or not. The stations is always just checking that whether the station is busy or not. If it is means see that there is no, that the channel is idle, there is no other packets or frames inside the channel, they can send the data. But here is a okay, this is not given here. Okay, so in p persistent, here the first thing, when a station is actually finding out that the line is idle, then different steps, some steps it needs to follow. So what are the steps? So with probability p, with probability p, the station sends the data, send the frame. So with probability p, and with probability 1 minus p, probability p with the stations can send the data, and 1 minus p, the probability q equal to 1 minus p, the station waits for the beginning of the next frame. Okay, next frame slot. It just the stations wait for 1 minus p amount of time. Okay, the probability 1 minus p, the station waits for the beginning of the next frame slot and checks the lines again. Okay, and if the channel is idle, the two cases can be arise. If the channel is idle, then again it can send the data with the probability p, and number 2, if the channel is busy, then what will happen? It acts as then if the channel is busy, then it has to be wait and to avoid the collision. Okay, so these things can be occurred. That means when the channel is idle, to send the data probability is p, and the the probability of wait is 1 minus p. Okay, and again each and every time it is sensing the channel. If it is idle, it can sense with the probability p, and if it is busy, then it can wait with the probability 1 minus p. Okay, and the whole here in the p persistent, all the means channel, the whole channel is divided into different slots. Okay, so these are the different persistence method for CSMA, carrier sense multiple access. So this is the flow diagram. So this is for one persistent, the channel, whether it checks the channel. If the channel is idle, station can transmit the data immediately, there is no waiting time, and if it is busy, then again it has to be checked the channel again and again. So this is a self loop. And here also in non persistent method, if channel is busy, wait a random amount of time. Okay, and if it is idle, then station can transmit. And for p persistent, if channel is idle, then probability outcome p, then station can transmit the data, and if it is busy, then the station needs to wait a slot, then again it needs to check the channel, and again doing the same thing. So p persistent, one persistent, and non persistent. P persistence means the sending the probability of sending our data is p, sending our data through the transmission medium is p. Okay, so this is the flow diagram of 3 persistent methods.